Question 11 from the 2019 Advanced Higher SQA examination in physics. A home improvement shop has a machine that can produce paint of any colour. Small amounts of pigment are added to paint in a tin, and the tin is then shaken to produce a uniform colour of paint, and the machine is shown in figure 11a. The tin is placed in the machine and clamped securely, and during shaking the oscillation of the tin in the vertical plane can be modelled as simple harmonic motion. The tin of paint has a mass of 3.67 kilograms, and the tin is shaken at a rate of 580 oscillations per minute. The amplitude of its motion is 0.013 metres. And for 2 marks we're asked to show that the angular frequency omega of the tin is 61 radians per second. So we can go to our relationship sheet and we can see that omega, the angular frequency, is going to be equal to 2 pi times f, and f is going to be the frequency of the oscillation, which we know is going to be 580 oscillations per minute. So a simple case of changing the oscillations into the standard hertz, which is oscillations per second. So we'll do that now. So all we have to do is say that the frequency is going to equal to 580, and it's going to be oscillations per minute, so we'll divide that by 1 minute. We'll put 1 minute here. Now we can write that 1 minute as the following. We can extend our line, and 1 minute we can write as 60 seconds in 1 minute, so we're really dividing by 60 seconds. So the 2 minutes cancel out, and you have got the frequency. If we'll do it over here, the frequency is going to be equal to 580 oscillations divided by 60 seconds. And that's going to give us a value of 97, if you do this in your calculator, per second, seconds to the minus 1. Of course, we could also write 97 hertz, but we'll leave it as 97 seconds per second at the moment. So just plug that f into your angular frequency formula. So omega is going to equal to 2 pi radians times the frequency, and we have the following: 2 pi radians times the frequency of 97 per second, 97 hertz, and we end up with 2 pi radians times this is going to give us a value of 60.9. If we do this in our calculator, and we'll put in radians, that comes from the pi part, radians per second, and we can just round up to give us the following: 61 radians per second. And that's going to be the angular frequency of the tin of paint shaking. Question 11 part 2. Calculate the maximum kinetic energy of the tin. Well, let's visit our relationship sheet again, and there it is there, and look down the equation to find out the kinetic energy, and we can see the one ringed kinetic energy EK is a half m omega squared bracket a squared minus y squared. But we're after the maximum kinetic energy, so what's the condition for that? Well, the maximum kinetic energy during simple harmonic motion will occur when the displacement is equal to 0. So we mark down that equation, EK, the one we've ringed, EK is going to equal to 1/2 times the mass times the angular frequency squared bracket the amplitude squared minus the vertical displacement squared. And we know also that when y equals 0, the displacement is 0, then the equation is going to reduce to the following. So when y, vertical displacement y is equal to 0, we're going to get the kinetic energy at its maximum. So EK, which is the maximum value, is going to equal to 1/2 m omega squared and times the amplitude squared. Now in our previous question we did work out the angular frequency omega, and we're also given the following pieces of information as well. So there's a piece of information we had. We had the mass of the can to be 3.67, we had the oscillation to be 61 radians per second, we worked it out, and the amplitude was 0.013. So all we have to do now is plug those numbers into the equation. So it's going to equal to 1/2 times the mass, and the mass is there to be 3.67 times the angular frequency squared, which is going to be in this case 61 squared. worked it out in the last question, times the amplitude squared. And the amplitude is going to be 0.013, so 0.013 all squared. And we work that out in my calculator, and we should end up with a value of 1.2 joules. So the maximum kinetic energy, 1.2 joules. But the main thing to remember here is that the maximum kinetic energy occurring during simple harmonic motion occurs when the displacement is going to be equal to 0. Question 11a continued, part 3. On the axis below, sketch a graph showing the variation of the kinetic energy Ek of the tin with the vertical displacement y from its equilibrium position. And we're asked for 3 marks to include the numerical values also. What we do know from our previous work there that we have the equation for the kinetic energy in simple harmonic motion, Ek is going to equal to 1/2 times the mass times the angular frequency squared times bracket the amplitude squared, take away the displacement squared. Remember, y is the vertical displacement. Now we know we can actually pin things in the graph because we know at a position where the displacement is equal to 0, we're going to get the maximum kinetic energy. And we worked that out. In this case, the maximum kinetic energy was given as 1.2 joules. So right away we can actually go and we can actually put in the value for that here. We can see there's going to be a maximum value here of 1.2 joules. Now what about the rest of it then? Well, we also know that when the position when the displacement y is going to equal to the amplitude, then you can see that the equation Ek becomes equal to 0. Ek will be equal to 0 because a squared minus a squared is going to give you 0. So we're going to have this position here. So when we have this as the amplitude, and the amplitude in this case was going to be 0.013, so 0.013 of a meter. That's the plus 1 there, and of course simple harmonic motion means it's going to be down here to minus 0.013 of a meter. So you can see the shape of the graph we've got. It's going to be a curve very much like that. It's going to go up and go down. That's the best I can do, showing you that at the maximum value up here you're going to have 1.2 joules, and at the amplitudes which are down here you're going to get 0 kinetic energy. And there's a little movie we can show you now to show you that happening when we use GlowScript, the VPython simulation program, which we should all learn. And this shows you in real time the kinetic energy varying with the displacement. And I'll show a little video now. Here we have a simulation of simple harmonic motion, a ball attached to a spring. We set it in motion, and you can see we have 2 graphs produced, one for displacement and one for kinetic energy. And the key point to watch from the 2 graphs is when we freeze the motion, we can see that the displacement, when it's at its maximum, is going to give us 0 kinetic energy. But when we have 0 displacement, we're going to have the maximum kinetic energy, what we did in the last part of the question there. So the key points are the following. From the graph you can see that when we have maximum displacement we have 0 kinetic energy, and when we have 0 displacement from the graph you can see that we're going to have the maximum kinetic energy as shown in the diagrams. Question 11 part B. A coin falls onto the lid of the tin of paint as it's being clamped into position. The coin loses contact with the lid during the first oscillation. And for 1 mark, we're asked to state the magnitude and direction of the acceleration of the tin when the coin just loses contact with the lid. Well, in this situation we have the lid here and we have the coin on top of it. And when it just loses contact with the coin, when the lid loses contact with the coin, then it will be accelerating downwards at a value of g. And of course the coin will also accelerate down with a value of g. So in that particular case they're going to lose contact because both of them are going to be in free fall. So the condition is that the acceleration of the tin can must be of the following. It must be acceleration must be equal to minus 9.8 meters per second per second. That's it in vector form. It means that for this to happen, the tin lid must accelerate downwards with an acceleration of 9.8 meters per second every second. 11b part 2. Determine the magnitude of the displacement of the tin from its equilibrium position when the coin just loses contact with the lid. If we go and look at our relationship sheets, you can see the equation at the top there, ringed. Acceleration equals d2y by dt squared equals minus omega squared y. So what does that mean then? We're going to use this equation. A, the acceleration, because we know that to be minus 9.8 meters per second. And that's going to go to the angular frequency minus the angular frequency squared times the displacement. And we already know all these values except for y, so therefore we can just rearrange for y. We can say that the acceleration divided by minus omega squared is going to give us the value for the displacement when the tin lid is accelerating at the acceleration of equal to minus 9.8 meters per second every second. So we'll put in the numbers and we can find out what y is. So y, the displacement, is going to equal to minus 9.8, and that'll be meters per second every second, divided by minus the angular frequency squared, which is going to be 61 all squared. We'll leave out the rad and just put in the second to the minus 2. That's it squared, so the 2 seconds cancel out, and you can see that 2 minus signs cancel out as well, and minus 9.8 divided by 61 squared, 2 minus signs cancel, and if you do that in your calculator, you get a value of 2.6 times 10 to the minus 3 meters. So that will be the value for the displacement, the magnitude of displacement when the acceleration downwards is going to be minus 9.8 meters per second every second. And to give that in some figures we can understand, times 10 to the minus 3 meters is a millimeter. So it's got to be equal to 2.6 millimeters. So that will be the amplitude where the acceleration is going to give us minus 9.8 meters per second every second, and the coin will lose contact with the lid.